Hi there, my name is Hayden Kane. This is EEE120 Lab 2, and let's go ahead and get into it. Um, this lab was about multiplexers, eventually leading up to an ALU. Um, so to start, our 1-bit 2-to-1 multiplexer is very, very simple. So we're going to just briefly go over it. You have two inputs, A and B. You have S, which is a selector. When S is 0, A input is going to go through Y. When S is uh, when S is 1, B is going to go through input Y. So you can see that A is not going through, however, B will. And so that is our 2-bit multiplexer. Let's go ahead and move on to our more interesting designs. Here is our 4-bit 2-to-1 multiplexer. So, like in our last lab, how for each binary bit we had to have a multiplex or we had to have a adder. Now we have multiplexers. So you can see that we have four input, four-digit binary number A and B. We have a selector, and we have output Y, which is also four-digit binary. So you can see when we go ahead and simulate this, let's just say A is 5 and B is 3. When select is 0, A is going to go through. When select is 1, 3 is going to go through. Pretty simple. Let's go ahead and uh, so here is our 4-bit 2-to-1 multiplexer. As you can see, let me just move this and me also. As you can see, when select is 0, A is going to go through. When select is 1, uh, when select is 1, B is going to go through, so on and so forth. Pretty simple. Pretty simple. Next, moving on to more interesting topics, we have our display, which functionally is the exact same thing, just that when we have an input on A and B, for instance, as well as Y, it's just going to show up in this digital display here, this 7-segment display. So this display displays given an input of four bits, 4-digit binary, it's going to go ahead and display this on this display. So pretty simple, pretty cool. And let's go ahead and move on to our not neg. So our not neg circuit essentially is taking the inverse and the negation of our input A. So let's see what's going on here. So given 3, as you can see, when inverse and negation are 0, it's going to go straight to our output Y through this incrementer here. However, when we activate invert, we're gonna ones complement our input A. So the inverse of 3, which is 0, 0, 1, 1, is 1, 1, 0, 0, which is C. Pretty cool. A is just gonna pass through like normal. However, things get interesting when we both invert and negate it, which is functionally acts as two complements. So we take the 2's complement of A. Uh, remember, A is 10, 1, 0, 1, 0. Take the 2's complement of that, which is uh, 0, 1, 1, 0, which is 6. Um, so yeah, pretty cool. So let's move on to our next design, which is our and add circuit. So this is kind of similar, kind of not really similar to our not negative. It is the other half of our ALU. Um, so let's go ahead and see what this does. When we have two inputs, A and B, which are again both four-digit binary, let's say A is 9, B is 3. Um, Yeah, we're doing a logical calculation. And so when we take 9, which is 1001, and it to 3, which is 1, sorry, 0011. The only using the truth table of and, we know that if A is 1 and B is 0, it's going to be 0. The only time that we get an output of 1 is when A and B are both 1. And so that's only present in our uh, the first digit, the first digit of our binary. So that's why our output is going to be 1. Um, Similarly, including a carry-in, that's just increasing the and between from two inputs to three. Now it's 1001 ANDed with 0011 ANDed with 0001. So it's going to remain the same, but that is the purpose of the carryout. When add is 1, we are going to, instead of doing a logical calculation, we are going to do an arithmetic sum. So now we're actually adding 9 plus 3, which is going to be C. Similarly, when pass is 0, passing just takes the is essentially our selector. So when pass is 0, our calculations go through. However, when pass is 1, like with a multiplexer, our A is going to go straight to our output. So when pass is 1, A is going to drive to Y, thus Y equals 9. Let's move on to our final circuit in digital, which is going to be our ALU. So our ALU is the combination of everything we just discussed. Um, as you can see, we have an inverter, an arithmetic, an input, and a pass. All of these function the exact same as the other circuits. Um, now they're just combined. We get options as opposed to having to do it in two circuits. We can do it in one. So like I said, it's just combining everything into a single CPU, which is an ALU. So let's just say, for instance, same thing. We'll have A is 9, B is 3. So because arithmetic is 0, we're doing a logical calculation, and of 9 and 3 is 1. Cool. If we invert this, things get a little interesting. This inverts 9. So invert of 1001 is 0110, sorry, 0110, which is 6. And so because arithmetic is 0, we're doing a logic logic thing, so our logic calculation. So and of 6 and 3 is going to be 2. And again, while all this go even during logic, we're doing logical calculations. This and add is still going on. So though we may not be using it, where it is always calculating our carry out or overflow. And so this ALU has 8 functions. And so let's go ahead and so our first function is going to be our two's complement with A. So as you can see, um, our test stimuli, we have A is A or 10 and B is 6. And as you can see, we have our our carry-in is 1, our invert is 1, our pass is 1, and our arithmetic is 1. So we're going to be doing a two's complement there. So the two's complement of A is gonna eventually equal 6. So here's our first function. It's going to be our two's complement. As you can see, we have a couple things going on here. Our invert is 1. Our carry-in is 1. We have throughout all of our test stimuli, pass is one, invert is one, and arithmetic is one. So this means that um, we're always going to be passing A to the output. We're going to be doing a arithmetic operation, and we also have a carry in for some, so or for portions of this test stimulus. So this invert means that we have to take the inverse or the negation of A, which is 6, and this pass means that we're going to take the inverse of A and drive it to Y. So that's why the inverse of A is Y, which is 6. And so this theme is followed throughout this two's complement stimulus. So let's move on to our next one, which is our arithmetic inverse of A. So as you can see, very, very similar structure here. Um, our invert is 1 and our arithmetic is 1, which means that we are going to be doing a arithmetic calculation with an inverse of A. However, this time we're not passing it straight to A, we're actually going to be adding it. So we have the inverse of excuse me, the inverse of 4 plus 9 plus a carry in of 1 for one of these test stimuli is going to give us 6, and then the inverse, the 1's complement of 3 plus 2 is going to give us f. Our next function, our third of 8, is going to be our arithmetic pass to A and B. Uh, so we throughout this function, our pass is going to be 1 and our arithmetic is going to be 1 as well. And so as we know, when pass is 1, A is going to Y. So this can be seen when A is 9, Y is 9. When C is A, or sorry, when A is C, Y is C, so on and so forth. The carry-in for the in this instance is as we're concerned with Y, does not really account for much. Let's go ahead and move on. Our next function is our very, very, very standard A to Y function. So here it's just pass. Again, like the last few. When pass is 1, we're taking A and driving it to Y. So when A is 5, Y is 5. When A is F, Y is F. Again, very straightforward. Moving on, we have our inverse of A function. So here we can see that invert is 1 and pass is 1. So first we're going to be taking the inverse of A. So A is F, which is 1, 1, 1. The inverse of that is 0, 0, 0. Passing 0, 0, 0 to Y is 0. So again, following that same pattern, 5 is 0, 1, 0, 1. The inverse of that is 1, 0, 1, 0, which is 10, which is A. And so again, that stimulus is the other test stimuli follow that same pattern. Moving on to our second to last function is going to be our logic function between A and B. So we have a carry-in. Sorry, we do have a carry-in for some of the stimuli. However, invert, pass, and arithmetic are all 0, which means we're not passing anything, we're not inverting anything, and we're doing logic. So very simple. 9 and 4, so which is 1, 0, 0, 1, and 0, 1, 0, 0. They don't have any, no digits have any voltage in common, so it's 0. And then that same comparison of and is followed through the rest of this stimulus. And last but not least, we have our logic with inverse of A. So very similar to the last one. We have no pass, no arithmetic. However, we are inverting. So first we have to invert A. So for instance, we have 4, which in binary is 0, 1, 0, 0. The inverse of that, excuse me, is 0, or sorry, 1, 0, 1, 1. And then we're going to AND that with 9. And the outcome of that is going to be 9. Additionally, we have to consider when we do have a carry-in, which in this instance we do, we also have to consider that when comparing the first digit of our binary. Um, so there's that. For another instance, we have 4. The inverse of that plus or ANDed with 3 is going to give us 3. Um, a interesting kind of a cheat code, I'm sure. Um, Actually, no, that's not how that works. Excuse me, never mind. Um, Given all of that, that concludes our lab for this week. Um, I hope I was thorough in my explanations, um, and quick. But I hope you enjoyed, and I will see you next time. Thank you.